Calculus has been described as the art of setting up and solving differential equations. So what are differential equations? A differential equation is an equation that expresses a relationship between an unknown function and its derivatives or differentials. There are two general types of differential equation. Ordinary differential equations, ODEs, which involve one dependent variable and one independent variable, and so ordinary derivatives, and partial differential equations, PDEs, which involve a dependent variable and two or more independent variables, and so partial derivatives. Some notations only explicitly show the dependent variable. The independent variable is understood by context. The Berkisto-Kronen logistic equations are two examples, though they could have been written in differential notation, which would explicitly show their independent variables. We will be focusing on ODEs in this anicast. An equation such as dy dx equals g of x, or dy equals g of x dx in differential form, is the simplest kind of ordinary differential equation. The radioactive decay equation is an example of this kind. The unknown function is y, which is also the dependent variable, and it represents the amount of radioactive substance present at any time t, the independent variable. The equation says that the rate of change in the amount of that radioactive substance over time, which can be measured in the number of atoms of the substance or its weight, is reducing at a rate that is proportional to the amount of the substance that is there at any time. That rate of decay is also dependent on what that substance is. A function is a solution of a differential equation on an interval if that function satisfies the equation at every point in that interval. In the case of dy dx equals small g of x, a function big G of x plus a specific constant is a solution if and only if it is an antiderivative of small g of x. Each solution big G of x plus a specific constant is called a particular solution of the differential equation dy dx equals small g of x. And the set of all particular solutions, infinitely many of them, which we can express as big G of x plus an arbitrary constant c, represents all solutions of the differential equation, or its complete solution. We can determine a specific value for the arbitrary constant, which means a specific particular solution, by applying an initial or side condition to the differential equation. A differential equation with an attached side condition is called an initial value problem. Graphically, the particular solutions of the differential equation are the integral curves of small g, each one vertically parallel to the others at each point. The complete or general solution can be represented graphically by any member of the family of particular solutions, with an added arbitrary constant to indicate that the curve's intersection point on the independent variable axis, which selects a specific particular solution, depends on the side condition. Let's look at an example. Find the function y, whose curve has a slope of 4x cubed at every point and passes through the point 1, 0. Since the derivative of a function represents the slopes of tangent lines to the curve at every point, the differential equation associated with this problem is dy dx is equal to 4x cubed, and the side condition is y of 1 is equal to 0, which represents the constraint put on the curve that it must pass through 1, 0. This problem is exactly the same kind that we solved in the first anicast in this series, of finding the general then specific antiderivatives of a function. Taking the antiderivative of the derivative of the function gives us the function. So y of x is equal to 4x to the fourth over 4 plus an arbitrary constant, which simplifies to x to the fourth plus an arbitrary constant. Applying the side condition, when x equals 1, y equals 0, so 0 equals 1 to the fourth plus an arbitrary constant, which simplifies to 0 equals 1 plus the arbitrary constant, and the value of the arbitrary constant is then negative 1. The particular solution of this initial value problem is then y of x is equal to x to the fourth minus 1. Verifying that our solution is valid by taking its derivative, we get dy dx is equal to 4x cubed, which is the original differential equation. Graphically, the solutions of dy dx is equal to 4x cubed can be represented by the entire family of basic quartic curves. each one a particular solution of an initial value problem. The equation of the curve representing the solution of this initial value problem is y of x equals x to the fourth minus 1. A differential equation is separable if it is possible to group all terms containing the independent and dependent variables separately. In other words, if y is a differentiable function of x, its derivative can be factored as the product of functions of x alone and y alone. To solve a separable differential equation, first write it in differential form, antidifferentiate both sides separately, then attempt to solve explicitly for y of x. For example, let's solve dy dx equals y squared times sine of x. We're writing the differential equation in differential form by multiplying both sides by dy over y squared. We get dy over y squared equals sine of x dx, or y to the negative 2 dy equals sine of x dx. Antidifferentiating both sides by applying the power rule to the integral on the left and the formula for the antiderivative of sine of x on the right, we get negative y to the negative first power plus a constant of integration equal to the negative of cosine of x plus another constant of integration. We can combine the constants, giving us negative y to the negative first power equal to the negative of cosine of x plus k, where k is the difference of the two constants that we had earlier. Multiplying both sides by negative 1, we get 1 over y is equal to cosine of x minus k. Taking the reciprocal of both sides to solve for y of x explicitly, we get y of x is equal to 1 over the quantity cosine of x minus k. Let's check this solution by going back to the first version and differentiating implicitly. We get negative y to the negative second power times dy dx is equal to the negative of sine of x, which is equivalent to 1 over y squared times dy dx is equal to sine of x, multiplying both sides by negative 1. Then dy dx is equal to y squared times sine of x, multiplying both sides by y squared, which is the original differential equation. Here are the graphs of three particular solutions of our separable differential equation, in which the constant of integration is equal to 3, 0, and negative 2.